So to learn about these distant worlds, we go ahead and we use the electromagnetic spectrum. We take the light from that star, we break it up into its constituent colors, we try to get that spectrum of the planet. And we do that via a technique called remote sensing. There are two types of ways, actually, of looking for different signs of life that we know of. Many of you who've maybe come to the Mars rover talks know about something called in situ detection of life. That's where you have the rock in your hand or in your robot's hand, and you're able to actually sample it and look for life. When we're looking for life around other planets, we have to use a technique called remote sensing, which is where we again look at the light from that planet, break it up into its constituent wavelengths, and study it that way. The reason we can learn about the planet is because as the light travels down through the atmosphere and then back to us, it interacts with the planet on the way down. It interacts with the atmosphere, it interacts with the surface, and it comes back and it tells us, as we look at it, what material it passed through, what material it bounced off. And so this plot, again, a little confusing, but I just want you to see the different colors and see how they're all very different shapes. And these very different shapes are indicative of different types of surfaces on our own planet. The gray one here is the reflection you get off clouds. You can see it's very highly reflecting. There's a little bit of water vapor you can detect in here. This one, the green, for a conifer forest, has a very sharp rise here. We'll talk about that later. This one for a desert, and this one for the ocean. So it's a tough task, but it is possible to try and disentangle all of these different types of spectra. So here are examples of spectra of planets in our own solar system. And what I want you to see here is, even if you don't understand what any of the features mean, you can see that these three spectra are different. Yes, they're different. So this one, apart from the colors are false. So this one here, you can see it's quite straight here, and then it goes into a whole bunch of wiggles towards the end here. This one is just a whole lot wiggly overall. And this one starts slow, comes up, and has actually very few features in it. So what we're looking at here are the spectra from these different planets and actually seeing the effect of molecules in their atmospheres in those spectra. So all of these wiggles here are from carbon dioxide. And if you look very carefully, you'll see that there's complementary wiggles down here that aren't anywhere near as strong, but this planet seems to also have carbon dioxide in its atmosphere. So we can go and look for these characteristic signs at the same position in the spectrum. And over here, this broad dip is actually due to iron oxides. So we know that we must be seeing to the surface of this planet because we're seeing iron oxides on the surface. And if you haven't guessed already, of course, these planets are Venus, Earth, and Mars. And Earth is interesting because its spectrum is so complex, because you see water vapor in the atmosphere, which could indicate that you have water on the surface of the planet, and because of this lovely spike here, which we're also very grateful for. This is the abundant oxygen in our atmosphere. So we ask, what makes a habitable world? You know, there's lots of worlds out there. Why are some habitable and others not? Well, it turns out that if we look at planets in our own solar system, there are several clues. Earth is habitable. Mars and Venus, maybe not so. Maybe Mars in the subsurface. The first thing we look at is planet mass. We don't want our planet to be too big because then it just accretes a huge atmosphere and becomes a giant planet. And we actually don't think that giant planets are likely to harbor life because of the huge convection cells they have in their atmospheres, which would, if you were a little molecule trying to form life, you'd be going up and down and you'd be frozen up here and overheated and pulled apart down here. So at least in our initial search for life, again, we try to give ourselves a break. We say we think it'll be the terrestrial planets, the Earth-sized planets, that are likely to harbor life. So we want to make sure that the planet is that kind of size, the same sort of size as the Earth, maybe up to 10 times the size of the Earth. And the other good thing about that is it means it can hold onto an atmosphere. An atmosphere is really important for making sure your ocean doesn't boil off. And also it means we can get something called plate tectonics, which is the circling of the crust of the planet, which helps us buffer or control the concentration of carbon dioxide in our atmosphere. And I'm sure you've all heard of global warming. It turns out that if you don't have plate tectonics on your planet, over very long periods of time, you can get carbon dioxide buildup, and that's not a good thing. So it's always nice to have enough mass to have plate tectonics. Mars, for example, doesn't have plate tectonics. It's too small. You need to be about a third of the size of the Earth to have plate tectonics over a reasonable amount of time. We also look at atmospheric composition. So what is the atmosphere made of? Because we want to look at how well it reflects light, how well it absorbs radiation and warms the surface of the planet. So that's a very important thing. Plus, again, you need an atmosphere to make sure that you don't boil off an ocean. You also want it in a kind of circular-ish orbit, because when it goes around its parent star, if it's in a circular orbit, it gets about the same amount of radiation all the time. If it's in an elliptical orbit, it gets hotter and cooler depending on when it comes close to or far away from its parent star. And we think if the planet has an atmosphere, we can tolerate a little bit of that, but you don't want to go too far from circular. And then finally, as in real estate, location, location, location. Really very, very important for knowing whether your planet is habitable or not. And there are two aspects of that. One is what kind of a neighborhood is it in? What kind of a parent star is it orbiting around? Is this a well-behaved parent star, or is this a psychopathic parent star that's going to be a problem? Secondly, you need to know, is it close enough to the star to be warm enough to have liquid water, but not so close that it'll boil away? Or is it too far away so it doesn't get enough radiation, enough heat, and it's too cold? So if we look at suitable parent stars, what does it take to be a parent star? The parent star, at least for the case of looking for life on other planets, we'd like it to live a reasonably long amount of time. The bigger stars are really live fast, die young. They go off in 100 million years up to 1 billion years or so. And so if you're looking for life to have climbed out of the primordial ocean and finally worked its way up to having a global effect on the planet, you really want more than 1 billion years. So stars that are significantly hotter than our sun die so fast that we really don't think they're good places to look for life around. We want the star to be stable, that is not to engage in this sort of behavior all the time, flaring and basically being a nuisance. So in that case, the younger stars tend to be that way. So you want to have your star at least 1 billion years old or so. And then in the end, this is preferred that your star be bigger than half the mass of our sun. And that's because if it's any smaller, the planet has to get so much in the face of the star in order to get enough radiation to be warm enough that in fact it ends up being tidally locked to the surface of the planet, and that can have its own problems for trying to maintain an equal surface temperature. So we kind of have a range in which stars could be. One thing we've also learned by looking out at the planets that have been found around other stars is that those stars that tend to have planets tend to have what we call higher metallicity. Now, to an astronomer, a metal is anything heavier than helium. Okay? So stars are made predominantly of hydrogen and helium, and then they have other stuff, like, lithium and carbon, nitrogen, oxygen, those sorts of things. So those things are termed metals by astronomers, though you and I breathe them, for example. So those stars that have higher metallicity, have those higher amounts of things like carbon, nitrogen, oxygen in their atmosphere, iron, tend to be better for finding stars around. So we think, well, that's a good place to look for more of them. So we tend to favor looking around what we call F, G, K, and M stars. And a G star is a star like our sun. Our sun is a G star. An F star is hotter than our sun, and the K and M stars are cooler. So we start with kind of the sun in the middle, and then we go a little bit hotter and a little bit cooler when we look around these different types of stars. So I talked about location. The other thing that's absolutely crucial is to at least find yourself starting out in what we call the habitable zone. Now, the habitable zone is the distance from the parent star that you happen to be orbiting at, if you're a planet. And this plot, what it shows is distance away from the star. So this is the planet's distance from its parent star. 1 AU is where the Earth is right now. And this shows the mass of the star, so how big and how bright the star is. These are little cool stars. Remember the M stars? K and M's are cooler. And these are the big live fast, die young stars, the A stars. So you can see that the habitable zone, if you're a very bright star, the habitable zone is much further away from the star. If you're a very faint, cool star, the habitable zone is much closer. So early on, in about 1993, Jim Casting actually did all of these calculations and determined if you knew the type of star, you could actually figure out where roughly the habitable zone around that star was going to be. And you can see that luckily for us, the Earth falls right in the habitable zone for our star. But you will notice that it's pretty close to the inner edge right now. Don't panic, it's all right. So what you also care about then is the continuously habitable zone for a star. And that is what region around the star stays habitable for a very long period of time. Okay, and for our solar system, that continuously habitable zone has a tiny span. It's about 5% closer to the sun than we are right now, and about 15% further away from the sun than we are right now. So you can see we're creeping up on the inner edge because our sun will get warmer, bigger, hotter with time, and so that habitable zone will have to move outwards, but we're already at the edge of it, so it's gaining on us. So you may have heard sort of in basic astronomy textbooks that it's okay, the sun's middle-aged, it's lived for 5 billion years, it'll live for another 5 billion years, don't worry about it. But the bad news is the habitable zone will run out faster than that. So the sun may become about 10% brighter in the next billion years or so, and the climate modelers say, as long as we, not even counting what's happening with carbon dioxide in our atmosphere right now, but just based on what the planet is doing, Earth may be uninhabitable in another 500 to 900 million years, so much sooner than you thought.